In my last video, I recreated my first 3D game using Raylib in Python. To do that, I used Raylib's own functions for drawing 3D objects with cubes or rectangular prisms representing wall blocks of a maze, a plane with a grid for the floor, and capsules to mark the exit and the enemy. In it, I didn't use any assets. All objects have flat colors with no textures. For shading, I made a hack using translucent blocks to darken the walls in the shadows, since Raylib's default shader doesn't do any kind of shading. The result looked kind of nice, but these graphics aren't all that great. In Raylib, if you want more interesting graphics, you need to add your own shaders to do the shading and other effects. In simplified terms, shaders are programs that run on the GPU instead of the CPU, performing geometry transformations and screen projection, rasterization, which is basically defining the color of each pixel based on position, texture, and light incidence, along with post-processing effects like bloom, blur, color grading, and wherever else you can imagine. The problem with shaders is that they are sometimes a bit counterintuitive, at least for people who have never dealt with them before. And besides that, there are other OpenGL issues that are quite confusing for beginners. But Raylib simplifies this a bit, so we can focus more on the shaders themselves without getting beat up too badly by OpenGL's complications. Usually, you need at least two shaders in Raylib: a vertex shader, which operates at the geometry level, and a fragment shader, which operates on the pixels themselves. I think that's what people call the render pipeline, probably because they are executed in sequence. These shaders are written in GLSL, the OpenGL shader language, which is very similar to C. You have to declare the type of each variable, add a semicolon after each line of code, and use braces to delimit functions, loops, and if and else blocks. For someone coming from Python, this kind of thing is a bit annoying to work with, but that's what we have. So after avoiding OpenGL for a long time, I decided to try adding some shaders to my Raylib game to better understand how this works and to give the game a more distinctive visual. In this video, I bring some of the main points I noticed during this process. And as an additional challenge, I decided to make everything compatible with WebGL, so my game can continue running on the browser. I will even continue from where I stopped in the last video. If you want, you can grab the code on each to follow along, link in the video description. To start, I'm going to do something that doesn't require shaders, but makes the shader results look better. I will add textures to the blocks and floor. But since drawCube and drawPlane functions don't work with textures, we need models. 3D models. But to create a model, we first need to create a mesh, which is the geometry, and Raylib has functions to create simple meshes like cubes, planes, cylinders, spheres, etc. So I will create a plane mesh and a cube mesh here. Then I can create models from these meshes. Now I need textures. In Raylib we can generate some images like gradients, white noise, purling noise, checkerboard, and cellular patterns. So I decided to create a purling noise texture. Also increase the image brightness a bit, and I will use the same texture for the floor and the walls. After creating the texture, we need to attach it to the models with model materials 0 maps PR material map diffuse texture. Now replace the drawPlane and drawCube functions with drawModelX, the extended version, since I will adjust the size of the models at render time. Here the parameters are the model, position, rotation axis and angle, scale and color. Now we have texture models. So let's start with the shaders themselves. To begin, I decided to create a directional light shader, which basically compares the direction each face of the model is facing, also called normals, with a parallel light vector, which simulates a distant light source, like the sun. I will create a file vertexshader.vs. In it, we need to define the version, and which version is compatible with WebGL. I'm not entirely sure. There are several OpenGL versions, but from what I researched, WebGL 2 is based on OpenGL ES for embedded systems, version 3.0. So that's what we will use here. Hashtag version 300 ES at the top of the shaders. Then we need to define the precision as high p float. Then define some ints, which are the data the CPU will send from the 3D models, like vertex positions, texture coordinates, colors, and normals. We also have uniforms, which are constants for all vertices, like the transformation and projection matrices. And finally, the outs, which will be the inputs of the fragment shader later, like the position, normal, texture coordinates, and color of each pixel. Inside the main function, we compute these outputs using vertex data and transformation matrices. And lastly, there's GL position, which, as I understand it, will be the position of the pixels in the screen space. With that, the vertex shader is ready. I will save it, and now we can create the fragment shader.fs. In it, we put the same OpenGL version and precision information. Now as ints, we take the outs from the vertex shader. As uniforms, we have the texture, the color, the direction and color of the light, which we will later define in the Python script. As out, we have the final color of each pixel, which is a vec4 with RGB and alpha channels. Inside the main function, I will normalize the normal of each pixel and compute the dot product with the light direction vector. I will keep a minimum light value of 0.25 or 25% as ambient light, so the sides opposite to the light don't become completely dark. The diffuse light intensity is then multiplied by the color light and converted into a vec4, with the last term, the alpha channel, set to 1. Then this vector is multiplied by the texture color, the vertex color, and the model color, finally giving us the final color. Now back in the Python script, first we load these shaders with the load shader function, passing the path of the vertex shader and then the fragment shader. Then we need to attach the shader to the models with materials 0.shader. But for the shader to work, we need to define the direction and color of the light and send them to the shader's uniforms. The light direction and color are Raylib 3D vectors. I will make the light point downward and a bit more to the x direction than the z direction. To send these vectors to the shader, first we need to get their locations with getShaderLocation. Then set their values with setShaderLocation. These uniforms can be set once per frame, for example, if you want the light to change over the course of the day, but you can also set them just once outside the game loop. I will also adjust the sun's position so that it aligns with the direction of the light we defined. I'll make the position always follow the player with an offset opposite to the light direction, so it looks like the sun is at a very distant point in the sky. We can see that the fake shadows I had added before don't line up well with the new sun position. And besides that, one block doesn't cast a shadow on the others, only on the floor. So the next step is to add shadows to our shader. For that, we will use the shadow mapping technique, which I have already used in my software render which I made a while ago. Objects are first rendered from the light's point of view, and with a depth buffer or Z buffer, we checked if there's any object in front from the light's perspective. We can leave the vertex shader as it is. We'll only adjust the fragment shader, where we will add some uniforms, the shadow map itself, and a matrix representing the camera from the light's point of view, plus the shadow map size. Here, before the main function, I will create a shadow factor function, which will take the current pixel position and reprojects it from the light's point of view. A bias is also added to compensate for depth texture errors depending on surface inclination. Then the resulting depth value is compared with the corresponding value from the shadow map texture. After the shadow factor is calculated in the main function, it's multiplied with the directional light value we had before. Now, back in the Python script, we need to create a texture with the depth buffer. For that, I created a function based on what I saw in a Raylib shadow map example. The function creates a frame buffer, replaces the default depth buffer with a depth texture, attaches it to the texture, attaches this texture to the frame buffer and binds it into a shader texture slot, allowing the shader to read the depth buffer as a shadow map. Here we also configure the shadow map uniforms and its size. I also created another function responsible for updating the shadow map. Here all the blocks, the exit capsule, the enemy, and the player are rendered using the light camera into the texture created by the previous function. First, I position the camera near the player with an offset in the opposite direction of the light, just like I did with the sun earlier. The target of the light camera will be the same as the normal camera's target, so it follows the player around. To start rendering the shadow map, I used begin texture mode with the texture as an argument. Then I clear it with clear background and start 3D mode with the light camera. Now we just need to get the view and project matrices from the light camera, render all the blocks in the map, the exit capsule, the enemy capsule, and I decided to render a capsule for the player as well so they have a shadow too. Then we can end 3D mode and texture mode. get the view and project matrices from the light camera, multiply them and pass them as the light VP uniform to the shader. And that completes the shadow update function. So I will create the shadow texture in the main function before the game loop, defining its size. Inside the game loop, I will call the update shadow function, passing the target equal to the normal camera target. Now I just need to create the light camera. I will copy the other camera and just change it from the camera perspective to camera orthographic. And it looks like I forgot the light direction parameter in the update shadow function, so I will quickly add it here. And finally, we have shadows, but their quality is pretty bad. We can try increasing the shadow map resolution, which helps a bit. We can also remove the fake shadows and translucent blocks I had added before. N is still horrible, but now I know what was missing. In the light camera I should have reduced the field of view. 60 is way too high, so I will reduce it to 20 so the light camera focuses more on the area around the player. So this looks much better now. But besides increasing resolution and reducing the field of view, another option is to use a filter when calculating shadows, sampling nearby positions to blur and reduce pixelated edges. This also helps with artifacts on walls called acne and Peter panning. For that, I will create a constant in the fragment shader for the number of samples and another constant with the samples themselves. These are semi-random positions around the origin to detect shadow edges. In the shadow factor function, I will comment out the return. Create a shadow counter variable to count how many points are in the shadow. Then I will loop through each sample, adding the offsets when checking depth in the shadow map. After that, the shadow intensity is calculated by dividing the number of samples in shadow by the total number of samples. Back in the Python script, we don't need to do anything else, just run it. Now the shadow quality is pretty good. If we want, we can even reduce the shadow map resolution. Well, maybe not reduce it that much. 1024 seems like a sweet spot. After that, I decided to add some glows to the agent, the exit, and the player himself, with colored point lights to add a bit of flair. Going back to the fragment shader, I will define at the top a maximum number of lights, to have flexibility in case I later want to add more. I will also add some new uniforms like the number of lights, their positions, and colors. I will also add a constant for the light radius or size. It could also be a uniform, but I was a bit lazy here. I will create a new function, pointLightGlow, that loops through each light, calculates the distance, compute attenuation, and sums the attenuated light color into a resulting color. In the main function, I will take this light and just add it to the lighting I created earlier. Back in the Python script, I will create the locations of the new uniforms, the list of colors, and the list of positions. For the light colors, I created a list with RGB values from 0 to 1 in sequence. That was the way I managed to make it work with Raylib. Since the number of lights and their colors won't change during the game, I will set them here. Inside the game loop, I will create a list with the positions of the enemy, the player, and the exit, which are then set in the corresponding uniform. Now we see a blue glow around the enemy, a kind of purple glow around the player, and a yellow glow at the exit. At this point I was fairly satisfied with the graphical improvements, so I thought this would be a good moment to check if everything was working properly in the browser. So in the terminal I ran the pigback command with the project folder and open localhost 8000 in the browser. After loading the game, to my surprise, the shadows don't work. It almost looks like the game is in night mode. It even looks kind of cool, but that's not what I made the shader for. From what I understand, the depth buffer works a bit differently in WebGL. I don't know if it's some kind of incompatibility with Raylib or pigback, but either way, the way I did it didn't work. So an idea that I picked up was to use a regular color texture to store depth values and pass that to the shader. But for that I will need a new shader to do these calculations, which will be called Shadow Pass. It is very simple and starts very similar to the first version of the fragment shader. Version 300 ES, high p-float precision, 4 inputs for normals, texture coordinates, pixel colors and pixel positions, and as output we have final color. Inside the main function I will create a dummy variable that's just a combination of input parameters. If I don't do this, WebGL throws some weird errors. Then I will take depth, which is glfragcord.z. I will store it in the RGB channels of the final color, and the alpha channel I will add 1 with the dummy multiplied by a very small value. I will save the shader and go back to the Python script where I need to load this new shader as shadow shader. For the vertex shader, I will use exactly the same one as the normal shader, just swapping the fragment shader for shadow pass. Then I'll add the shadow shader as a parameter when I call the update shadow function in the game loop. I will also copy the line where the shader is attached to the cube model before going down to the functions. In the function where I create a depth buffer, I will remove all the depth related parts, since now we will be working with colors. But in the part where the texture is enabled, I need to replace depth with texture. In the update shadow function, I will also add the shadow shader. And before starting 3D mode, I will switch the cube model shader to the shadow shader. After finishing 3D mode, I will switch it back to the normal shader. I won't do this for the floor because the floor doesn't need to be rendered in this case. It doesn't cast shadows on other objects. I will also change the clear color of the texture to white, change the capsule colors to black. Now we can test this new depth buffer. It kind of works, but for some reason shadows on walls that are farther away disappear. I suspected this had something to do with the depth value range, so I decided to multiply the depth by 30 in the shadow pass, doing the same thing in the shadow calculation in the other fragment shader. Now distant shadows work, but several lines appear on the walls that don't have shadows. This seems to be a problem with the bias value, so I decided to reduce it a bit. It works a bit better, but now different artifacts appear on the edges of shadowed walls. That problem is due to low precision, but before making more changes, I will test again in the browser to see if we have reasonably decent shadows working. Running the pigback command again in the terminal and opening the page in the browser. And yes, everything is working, at least the same way as in the desktop version, so we have made progress. But we still have a relatively easy option to improve these shadows, which is to use the green and blue channels, not just the red channel of the texture. In theory, we could use the alpha 2, but then we will need to disable alpha blending, and I don't really know how to do that. If you know, please tell me. Before doing that, I will also slightly change how depth is calculated, to try to increase precision a bit. Going back to the vertex shader, I will add an out called vdepth or vertex depth. It's calculated by dividing glPosition.z by glPosition.w. Then I will go to the shadow pass and add the in for vdepth and add two constants, one for bit shifting and one for bit mask, which will be used to distribute the depth precision across the RGB channels. It seems to be a fairly standard technique. In the main function, I will take vdepth and bring it to the 0 to 1 range and also multiply it by 30. I will create a new vector and do the bit shift and bit mask magic, and put the corresponding RGB channels in the final color, keeping alpha as 1 and adding dummy multiplied by a small value. In the fragment shader, I will also add a bit shift constant to undo the shadow pass magic and recover the depth value. When sampling the texture, I need to read the RGB channels instead of just R and store them in a vec3 instead of a float. When comparing with the calculated position, I will take the dot product of this vec3 with the bit shift constant. Testing the Python script again, it doesn't look like much changed, but that's because now, with higher precision, we can reduce the bias in the fragment shader. And with that, those edge artifacts decrease significantly. Now all that's left is to test again in the browser to see if it is still working. And to my relief, it is. Now we have textures, directional lights, shadows, and points of light glow working in the game. I won't lie. It took a bit more than I expected, especially the WebGL part. But even so, I really liked it. I will update the version on itch.io and also make the intermediate versions of the Python scripts and shaders available there, in case you want to take a look. I hope you enjoyed the video, thanks for watching, and I see you next time.